Hello, I am Shruti Parthasarathi from University of Florida from the Electrical and Computer Engineering Department, and I would be presenting on the topic Mechanism of Dynamic Modulation in Changing Channel Conditions as a part of the project in the Wireless Communications course. One of the major factors that determines the quality of wireless signals is the communication channel. Since the communication channel in a practical scenario is continuously being modified, the highest throughput can be achieved if the scheme is tailored for a particular value of the channel gain. However, a fixed modulation scheme over the changing channel is proved to produce lesser throughput. This project aims to study the various modulation schemes and their bit error rates and comes up with a comprehensive algorithm to determine the best modulation scheme for a particular value of transmit SNR by developing a mapping from the SNR value to the best possible MCS rate provided the BER constraints are met. There has been a lot of advancements in digital signal processing and in large-scale integrated circuits over many years, and this has led to the development of faster, low-cost, and power-efficient modes of communication. Other reasons, including high data rates, better error detection and correction techniques, robustness of the transmitted signal under varying channel conditions, easier multiplexing techniques, better multiple channel access techniques, etc., have led to the success of digital communication over analog communication. Improvements to error detection and correction techniques, encoding and decoding mechanisms, signal conditioning, multi-carrier techniques, and equalization, along with the advent of digital modulation schemes, have made it possible to achieve very high-quality, low-cost solutions in the fields of digital communication system. All these factors have made digital communication to be the most suitable choice for wireless applications. The different parts of a wireless communication system consists of majorly a transmitter source which converts the information to a digital format, a source coder in order to remove the redundant data bits and compress it to the most efficient form of representation, a channel encoder in order to add extra parity bits to protect the bits from getting corrupted when subjected to noise, a digital modulation system which converts the binary data into waveforms, communication medium, and the receiver system which decodes the received analog signal into the required data formats. The two major types of digital modulation techniques are linear and nonlinear modulation. Although the linear modulation technique is susceptible to more fading, it has higher spectral efficiency when compared to nonlinear modulation, which is naturally more robust to corruption and fading. The corruption of data could be attributed to many possible factors, including the modeling of the channel, which might change with time, the attenuation of the signal that may be caused due to the properties of the antenna, thermal noise, intermodulation noise, and channel fading, which may be caused due to the destructive interference. These factors of noise will reduce the quality of the signal at the receiver, making it very difficult to comprehend the received signal, which will lead to erroneous decoding of the data. The signal-to-noise ratio, or SNR, also depends on the power of the transmitted signal and the channel power gain along with the noise power that gets added. The types of modulation schemes under consideration here are BPSK, QPSK, 8 QAM, and 16 QAM. There are multiple problems that can be listed for a wireless communication system. A typical wireless communication channel causes delays in the signal components and also causes reflection of signals, which results in the receiver getting multipath signal components that tend to affect each other randomly. The outcome of this is the fading and attenuation of the signal. This has high probability of the receiver to decode data that is erroneous, leading to lower throughput. Channel fading has always been a problem and has been in the highlight for very many decades. However, if the transmitter power is made large enough and if the probability of error is made low so that it is within acceptable levels, then the throughput can be increased. Nevertheless, there are a lot of inefficiencies with this approach. Another method is diversity transmission, where the signal is transmitted over multiple channels with statistically independent fading. Here, although it achieves a considerable improvement in performance, this method has not proved to be cost-effective due to the high equipment costs and also the increased bandwidth accompanied. Thus, For high data rates to be achieved, robust and spectrally efficient methods of modulation and coding are required in order to combat the effects of flat fading channels. In a situation of a reciprocal channel, if the channel characteristics can be estimated by the receiver and the receiver sends some pilot signals to the transmitter, then the transmitter can in advance be aware of the channel and can adapt its transmission methods accordingly. This method, which are tailored to specific to the channel at that point of time, will give higher data rates. However, since the transmitter modulates the signal based on the worst case scenario for that particular channel characteristic that it is received, the method will lead to low utilization of the channel. Thus, adaptive methods have to be employed in order to maximize spectral efficiency and the throughput to have high channel utilization and achieve high data rates. The main focus of adaptive modulation techniques is to maintain a constant EB by N0 value and correspondingly varying the constellation size, modulation and coding schemes, transmitted power, and a combination of these factors. Although techniques have been found to be very effective and efficient, there are practical constraints to its usage. If the communication is modified at a rate faster than it can be estimated at the transmitter, then adaptive schemes do not perform well. In this presentation, we shall see the analysis of a novel method in using a simple algorithm that determines the best modulation scheme that can be used for a flat fading channel where the channel characteristics change for every time slot. This results in utilizing the channel to a high level of efficiency and also achieving high data throughput rates while satisfying the BER constraints. There are multiple modulation schemes that could be used by the transmitter module. Here specifically we analyze BPSK, QPSK, 8 QAM and 16 QAM as mentioned earlier. Also another point to be noted is the binary sequence for MQAM the binary sequence of data is converted to gray coding representation in order to minimize the errors. In gray coding, the differences in values that are received at the receiver end cannot go through the states that are not a part of the gray code sequence for the given number of input bits. Thus, gray coding is an efficient and clever way of representation in order to minimize the probability of error. The communication system under consideration in this paper and project has been shown here. This channel is a discrete time system which has a time varying gain and an additive white Gaussian noise. The channel is assumed to be a Rayleigh flat fading channel with coherent detection. Since the channel is assumed to be flat fading, the bandwidth of the signal is much lesser than the bandwidth of the channel. This gives an advantage of the spectral characteristics of the channel being preserved over time, although the amplitude of the signal may vary with time. Thus, the probability density function of the flat fading channel is given by the expression as shown here. The characteristics of the flat fading channel is also shown here. The exponential distribution of the channel is considered due to the multipath effects of the channel. Also, the rate of variation of the channel determines how frequent the transmitter should adapt to the changing channel condition and to choose the best modulation scheme. In order to account for the randomness of the noise in the channel, which could corrupt the transmitted signal, it is modeled as additive white Gaussian noise, where the random noise gets added to the signal. Since it is additive white Gaussian noise, it is flat for all frequencies. Thus, the actual communication channel can be described by the equation as shown on the screen. Y of t equals S of t into H of t plus N of t. The experimental system at study consists of a transmitter, a wireless communication channel, and a receiver. The system model is as described in the previous section. In the previous slide, the channel, which is considered to be a Rayleigh flat fading channel, is assumed to have a noise variance of 1. Also, the simulation has been run for 10 power 5 time slots. The main idea of the simulation is to demonstrate the maximized throughput that has been attained subject to BER constraints. The communication system transmitter source can generate random input data bits that are subjected to varied EB by N0 values. Now let me describe the algorithm that is used. Here we mainly have the transmitter symbol SNR that is determined the Rayleigh flat fading channel power gain is expressed as an exponential random variable. The receiver symbol SNR is determined by the product of transmitter symbol SNR and the channel gain. The bit error rate is determined for all possible modulation schemes. How is this done? This is done by running simulations of a communication system on MATLAB. The transmitter source generates a random bit sequence. It is modulated and scaled by the channel gain and the TX symbol SNR. The additive white Gaussian noise is also added to the channel. The bit error rate is determined for 10 power 5 time slots once the signal is received at the receiver and for the signal to be received at the receiver end. So basically this entire, there are 10 power, there are a set of signals that are generated and the BER is estimated, and it goes on for, this iteration goes on for 10 power 5 times. Now the BER is estimated for each case, and then the SNR thresholds that meet the BER constraint of 0.01 are determined, and the corresponding modulation scheme is mapped to particular SNR values as shown here. So basically it can be seen that so these are the gamma values or the SNR values, and then it's seen that if your received signal SNR is lesser than gamma 1, then there is no point in transmission because you would be receiving an erroneous data. So if you transmit data between, so if the SNR is between gamma 1 and gamma 2, then a BPSK scheme could be employed. If it is between gamma 2 and gamma 3, then QPSK could be employed. Between gamma 3 and gamma 4, an HQAM scheme can be employed. So in this way, it can be increasing. So here this also shows that the number of bits per symbol are increased. So in this way, if we transmit, we are guaranteed of the packet passing if we send it at a particular modulation rate, and hence this would maximize our throughput. So all these results of the gamma values are stored offline in a .mat file in MATLAB. These could also be run online, but just that it would consume a lot of time for every simulation. Then comes the actual part. The actual simulation for various values of the TX-SNR is run, and it is assumed that the data, if modulated according to the mapping stored, reaches successfully at the receiver end, and the bits per transmission is determined for each iteration. Now the same experiment is run with various constant bitrate schemes, and the results are also plotted. The experiment is repeated for various values of the channel parameter lambda. Let's see the results now. The results and the simulation would be shown in the next video. Thank you.